Bismillahirrahmanirrahim. Welcome to the Electrical Engineering YouTube channel. In this channel, you will be able to learn the fundamentals of transformers, their working principles, their construction, and their working, and their types with respect to their design. So, a transformer is a static device which is used to step up or step down AC voltage while keeping the power and frequency constant, and it works on the principle of electromagnetic induction. And electromagnetic induction has further two types. First type is called mutual induction, and the second type is called self induction. In a two winding transformer, the phenomena which is taking place is a mutual induction, whereas another type of transformer is auto transformer, and in that type the phenomena of self induction is taking place. So Faraday's law of electromagnetic induction can be stated that EMF induced is directly proportional to the rate of change of magnetic flux, and phi m is actually the magnetic flux. If we apply a DC voltage across the transformer, there will be flux which will also be constant in nature. For that type of DC excitation, the rate of change of flux will be equal to zero since the flux is constant. So there will be zero EMF which is induced across the secondary of the transformer. So transformer cannot be operated for a DC excitation, and we only need an AC voltage to cause an induced EMF across the secondary. So this is the construction of a two winding transformer, and this is its symbolic diagram. This is the primary winding, this is the secondary winding, and in between there will be magnetic flux which will be produced due to the current flowing through the primary, and that magnetic flux will be alternating in nature, and that flux will be actually linking with the secondary winding. So due to that alternating flux in the secondary winding, EMF will be induced, and in this case there is actually air between the primary and secondary winding, and air is used to carry the magnetic flux. So we know that the permeability of air is very small. So due to this reason, the magnetic reluctance offered by the air will be very high. So in that case, most of the flux will be leaked into the air. So in order to minimize that leakage flux, an iron core can be used, which can be shown in this figure. So this is iron core, and in this leg or in this branch, we have the primary winding at which we will apply the alternating current voltage, AC voltage, and that alternating flux will be flowing through this iron core, and it will be passing through the secondary coil. And due to this alternating flux, EMF will be induced across this secondary winding, and in that case the magnetic reluctance of the iron core will be very small, so maximum flux will be linking with the secondary, and the leakage flux will be minimum. So this is all which has been discussed, that flux links with the secondary winding and it induces EMF. So this is the mathematical form of the Faraday's law, and induced EMF is proportional to the rate of change of magnetic flux. Is this negative sign is due to the Lenz's law, and Lenz's law can be stated as the induced EMF is always opposite to the cause which produces it. So if we take the derivative of this flux, uh, then the derivative of that flux will also be sinusoidal in nature, but that derivative of the flux and the induced EMF, they will be 180-degree out of phase with each other. So that 180-degree out of phase is represented by this negative sign. In order to remove this proportionality, we have to introduce a constant, and that constant is called number of turns across the primary winding and number of turns across the secondary winding. So if we take the ratio of this expression and this expression, the derivative of the fluxes will be cancelled out, and we will have only E1 over E2 equal to N1 over N2. And there are two types of transformers. First type is called core type, and the second type is called shell type. So this is a core type transformer, and this type is also a core type transformer, but in this case we have two different legs for the primary and the secondary windings. So if we actually do the winding in such a way that part of the primary winding is done at this leg and part of that primary winding is done on the second leg. Similarly, part of the secondary winding is done on this left leg and part of the secondary winding is done on this right leg. So in that case, the flux which is produced in the primary will be directly linked with the secondary without passing any, without flowing through any region of the core. So similarly, across this right leg, maximum flux produced in the primary will be linked with the secondary. So in this case, the leakage flux will be further minimum. So this is another core type transformer, and in this transformer we have actually changed the sense of winding. And this is a type of a shell type transformer. So this transformer, its shape is like a shell, and we have three legs over here, and there are two hollow or air regions in between these three legs. So primary winding is done on this leg, and secondary winding is also done on this leg, and the flux which is produced in the primary will be linked with this secondary, and there will be very small leakage flux again in this case. So these designs offer less leakage flux, and in transformers, power remains the same. So VPIP is the primary power, VSIS is the secondary power. So I have to specify that these are the apparent powers. So these are the apparent powers which are simply the product of altered AC voltage and current. So these powers are same at the primary and at the secondary windings. So Vp over Vs is equal to E1 over E2, and E1 over E2 is the induced EMF across the primary and the secondary windings. And from this above expression, Vp over Vs is equal to Is over Ip. So Is over Ip is written over here, and that Is over Ip is equal to Vp over Vs, and Vp over Vs is equal to N1 over N2. So this is another expression which we have obtained for the current transformation. Similarly, Vp over Ip is equal to the resistance of primary winding, and Vs over Is is equal to the resistance of the secondary winding. And if we divide Rs with the Rp, so Rp over Rs will be equal to Vp over Ip divided by Vs over Is. So it will become multiplied by Is over Vs, and so this can be written as Vp over Vs and Is over Ip. Okay, so Vp over Vs is equal to N1 over N2, and Is over Ip is also equal to N1 over N2. So Rp over Rs is equal to N1 over N2 square. So these are the resistance or impedance transformations, and this is the current transformation, and this is the voltage transformation. So these transformations will be helpful in determining the parameters when we refer the equivalent circuit of the transformer either to the primary side or the secondary side. So these transformations will be useful in that situation. So this N1 over N2 is called the turn ratio, and it is represented by A. And transformer can be used for impedance matching purposes to transfer maximum power to the load. So if we choose such a turn ratio that the Rp over Rs is equal to N1 over N2, and we can select such a combination of the primary and the secondary windings so that their ratio corresponds to the load after the transformation, and that load, if it is equal to the source impedance, then maximum power will be delivered to the load, which is called maximum power transfer theorem. So if we achieve such a turn ratio combination, then maximum power will be delivered to the load, and this is called impedance matching. So if we match the impedance, uh, load impedance with the source impedance by using a transformer, then it will be helpful for maximum power transfer. So these are different shapes which actually can be used to design a transformer, either core type or shell type. So this is E shape, this is I shape. If we join this E and I together, we get such a shell type design of a transformer. Similarly, This is L shape and this is inverted L shape. If we join these two designs, we will get a core type configuration. And for example, in this figure, we can see that this L shape and this inverted L shape, they are joined together, and butt joints can be used, which will offer a low magnetic reluctance path. So if we use this butt joint, they will be joined or they will be sealed very strongly with each other, and the flow of flux will be very easy. There will be very small reluctance. So this is the primary winding, this is the secondary winding, and again we can do such a practice for this shell type transformer, and here butt joint will be applied. So multi-layer winding can also be used in a transformer, and the multi-layer winding is very beneficial, and in that case one winding is done first and then the other winding. So normally high voltage winding is done in the lower layer, and the low voltage winding is done on the upper layer, and in between there is an insulator, so that the primary winding and secondary winding both are electrically isolated from each other. So if we do now from this turn ratio expression, we know that V E1 over E2 is equal to IS over IP, and we know that E1 over E2 is equal to N1 over N2. It means the induced EMF is directly proportional to the number of turns, and the side at which more number of turns are present, there will be more voltage, and at the side where less number of turns are present, there will be less induced EMF. So if we have 100 turns at the primary and just 50 turns at the secondary, and if we apply 230 volts at the primary, then we will get 115 volts at the secondary. So since the number of turns across the at the secondary side are half, so we will get half voltage. So in this case, if we are doing multi-layer winding, and we have to do the high voltage winding first in the lower layer, because the lower layer will have a smaller diameter, and we can uh, use very small copper, very small quantity of copper, if we are doing the winding with a smaller diameter, and we will achieve more number of turns with small copper. And for the low voltage side, the diameter will be high, but we have to do the winding at the upper layer, and number of turns will be less in that case, but the diameter will be bigger than the diameter at the lower layer, but the number of turns will also be less, so we can save a substantial amount of copper for doing the winding if we are doing the multi-layer winding at the transformer. So this is the configuration, and you can see this is the lower voltage and this is the low voltage slot, this is high voltage and this is also high voltage slot. So in across these slots, high voltage winding will be done, and across these outer slots, low voltage windings will be done. So a transformer can be used either in step up or step down configuration by selecting appropriate sides. And insulating materials, they are very important to determine the lifetime of a transformer. They are non-inflammable and they don't decompose into inflammable gases in the presence of arc. The most commonly used insulator is pyrochlore, and these insulators are actually oils. So we have heard that an oil is used in transformers. So the purpose of that oil is to produce dielectric strength, and it is also used to rapidly quench the arc, and it should be a stable dielectric. So pyrochlore is a type of oil which is used in transformers. And distribution transformers, oil is used for cooling and insulation purposes between two windings, and it is also used for arc quenching. So this is a step up transformer. Here we have smaller number of turns, and here we have a larger number of turns, so there will be less EMF across the primary and high voltage or high EMF at the secondary, and here we have the opposite scenario. So finally we will derive the expression for the induced EMF at the secondary of the transformer. So for that purpose, we have to first define the form factor. Form factor is actually the ratio of RMS value to the average value, and RMS value is equal to 0.707 times Vmax, or Vmax divided by square root 2, and average value of a sinusoidal waveform is 0.637 times Vmax. So the ratio will be equal to 1.11. So this is the EMF equation of a transformer. We have N1 primary turns and 2 are the number of secondary turns. Phi m is the maximum flux and it is equal to flux density multiplied by the area, and F is the frequency. So this is a sinusoidal flux which has been produced in the transformer. In order to calculate the average value of this flux, we have to consider either the quarter of a cycle or half of a cycle. If we consider the full cycle, then the average value will be equal to zero, because it is uh, because it is positive, same positive as it is negative. So either consider half cycle or a quarter cycle and divide it by either the half time period or a quarter time period respectively. So average rate of change of flux is equal to phi m divided by T by 4. So from here to this point, the flux has been changed from 0 to phi m, and from this point to this point, the time has been changed from 0 to T by 4. So their average value will be equal to phi m divided by T by 4. So T by 4 can be replaced by 1 over 4f, and average EMF per turn in that case will be equal to 4f phi m volts. So since the flux is sinusoidal, we have to consider the form factor first, and form factor is equal to 1.11, and it is equal to the RMS value divided by the average value. So this average value can be multiplied by this 1.11 to get the RMS value. So uh, that expression, the RMS value of this induced EMF can be written as 1.11 into 4 FIM. Since we have calculated the average EMF per turn equal to 4 FIM, so if we multiply this average value of the flux with this form factor 1.11, we will get the RMS value. So how come this average value equal to 0.637 FIM? We have to do this integration from 0 to T by 4 quarter of a period and divide it by that quarter of a period and integrate, put the limit. So finally we will get 0.637. Similarly, we can calculate the RMS value of this flux by doing this integration, which is equal to 0.7075 m. So their ratio will be equal to 1.11. So this is the RMS value of the induced EMF for a single turn. So if we have n1 number of turns at the primaries, then in that case, the induced EMF at the primary side will be equal to 4.44 F and 1 phi m. So 4.44 F and 1 and phi m is equal to Bm multiplied by A. Similarly, E2 will be equal to 4.44 F and 2 multiplied by phi m, and phi m can be replaced by Bm multiplied by A, and E2 over E1 is equal to N2 over N1. So by taking the ratio of E2 to E1, all other terms will be cancelled out and we will get N2 divided by N1, and that will be equal to the turn ratio. So that is all about our today's basic discussion on transformers, and I hope you have enjoyed and understood the concepts which has been discussed in this video. So for watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.